Good afternoon. It's a pleasure to be here. Thank you, Energy Simulation, for organizing these events. Thank you all for attending here and online. I'm going to talk today about the subject of my chair. So first of all, I will present very briefly our group, which is UNICAMP of University of Campinas, which is dedicated to model-based simulation and management, with a strong integration with geoscience, production, engineering, economic evaluation, carbon intensity calculation, optimization, and data science. So we have students and researchers working in all these areas with the objectives of developing people and new methodologies for all these areas integrated. We are now about 75 people, including students, researchers, administrative people, professors, and IT people. But today I'm going to talk about one particular subject of all the areas we have in research there, which is intermediate step to the digital fields, which is the model-based management in 3 stages. In order to get a digital twin, which is our final objective of this project, we need to separate the optimization process in 3 different stages. That's what I'm trying to show you today. So the 3 stages are the life cycle, which is considered the entire life of the field. Then the short term, which is about 6 months to 1 year, which is the cycle that we normally consider for analysis in a model-based. And also the real time for changing the solution every time you have any unexpected result or operational problem or so on. So the motivation for that is that companies in Brazil ask us to use reservoir simulation models not only for life cycle management, but also for short-term management, in order to use them in digital field applications, and also because the life cycle optimization, as we have seen in Leonardo's presentation as well, is very complex, it's very time-consuming. We have many variables to optimize, consider a lot of uncertainties, a lot of risk. So it's a very complex problem. So if you want to use these models in the short-term and real-time optimization, that will take too much time. So the objective is to develop a methodology to improve the quality of the short-term production forecasts and decisions, and if possible, integrating that with machine learning and artificial intelligence to make it faster. So the final application is to use this real-time management in digital fields, and if possible, to develop a digital twin of the reservoir to take fast decisions. At the end, of course, we want to contribute to more efficient energy production, especially from the pre-salt of Brazil. As Leonardo showed, that is very important for us there. So this is a scheme that I show every year here, but just to initialize the explanation, the closed-loop field development and management process. I'll not explain all the details here, but basically we have 4 colors here. The green color is dedicated to build the models, so we have students and researchers trying to build the best model for each application we have, including the multi-fidelity models, because for life cycle and for short term, the models are not exactly the same. The best models are not exactly the same. Once we have these models, and we have dynamic data, we have this red part, which is the data simulation or history matching part, where we try to improve the quality of the models by using data. Once we have these models, we go into the blue part, which is the production optimization of the life cycle, considering the variables until the end of the reservoir's life. And then that's the part that we are changing nowadays, because that used to be the selection of the production strategy for the field. Now it's not anymore. This blue part doesn't go into the reservoir anymore. So it has to go through the gray part and black color here, which is the short-term production optimization and the real-time optimization. So just to summarize, we are trying to do is to divide this in 3 different stages. The blue stage is stage 1 is the life cycle optimization. The gray one is the short-term decision. And when we have the short-term decision can be implemented directly in the field, unless we have any unexpected result or operational problem, anything. If you have anything different that we expect, then we go into the real-time optimization. we use the dynamic data not only nowadays to do the history matching and data simulation, but also to feed the artificial intelligence problems to help in this real-time optimization as well. And of course, as I will explain, we have two different arrows here because as we are dividing this in 3 different stages, the stage 1 is much more simplified than we used to do. It's a very simplified to get approximate solutions because the optimization I will do in the gray part. But of course, in parallel or offline, we can run the complete life cycle optimization to get all the uncertainties, all the risk analysis, everything we used to do. Because anytime we find the different solutions and a better solution than before, I can feed the stage 2. So, So this part here will feed good solutions, new solutions for every time we have these new solutions that is running in background. And of course, every time I find a different solution in stage 2, that means that they are not compatible, stage 2 and win. So I have to go back and in this other thing to check if the new solution, new management rules are good for life cycle as well. And of course, that stage 3 will happen only if I have some operational noise or something different that I was expecting. Otherwise, I can implement the solution for stage 2. So just to give an idea, a more graphical idea, we build the models in these green parts, then the blue parts will find solutions for the entire life of the field, but just approximate solutions. I will not find the exact solution in this part. This will will be used as set points for the real optimization that we do. In the short-term optimization, we consider only the variables that we're going to implement in the next loop of the closed loop. Then we have much less variables. It can be a much faster process and much more appropriate process to decide what we are going to do with the variables that we are going to implement right away. And of course, every time we have operational problems, we can change this management by using this real-time optimization. And from time to time, I update the model in this red part in the data simulation. Every time I change the model, I have to do everything again. Just to give some ideas of the 3 stages, the life cycle optimization will include all uncertainties, all risk analysis, all the probabilistic decisions we use to take. The models are very complex and computational intensive, so we can run this process offline. We initially get an approximate solution, and then we keep running this offline. Every time we have a new solution, we can feed stage 2. These approximate solutions will be used as set points for the closed loop cycle optimization. And in background, I can run this, I can check all these long-term effects. The closed loop optimization is a short-term, usually for us, at least for the pre-salt, of course, each field will be differently, but we used to do 6 months to 1 year. And we are also checking, and we have published some results showing that for these short-term effects, the effect of the uncertainties are not so huge as they are in the life cycle, so we can use more deterministic approaches. In some cases, even a deterministic model, which is the best model to take the decision. So it's even faster because I use just one model, and I consider only the variables that are going to change in the next loop, and also a very short term for a simulation. So I can do it very fast. So the life cycle, if I change any rule at this point, I have to check if these new management rules are good for life cycle as well. So I keep changing information between stage 1 and 2. And every time I have any modification, I will show some examples of operational problems. It can be some wells that are closing, pumps that does not work, or unrevealed uncertainty. Anything that's different that I was planning, I can do a very fast real-time optimization. This part we are doing manually nowadays, but the idea is to do this automatic. And when we finish that, we plan to have a digital twin of the field. So as a general methodology, what we did so far to get at this digital twin is that we had to improve the quality of the simulation models for short-term forecasts. This took much more time than we expected because the models are not the same. The effects of life cycle and short term are different, so we have to have a little bit of different models, and the history matching and parts is a little bit different as well. We had also to integrate with the production facilities because the boundary conditions for the wells are very important for short-term effects. And then we had to divide our type of variables in different categories because we have a lot of things to consider. So we first defined what is a human intervention-free operation if nothing happens. Then we have to impose some prescribed operations, which are some operations that we know that are going to happen, especially when we use machine learning to predict the short-term forecasts. Anytime we have these prescribed operations and something that we know they are going to happen, we have to impose these solutions to the digital twin. And also we are using deterministic approaches nowadays. We started doing probabilistic, now we are doing deterministic to do it much faster. In parallel, we are studying techniques to do this even faster using machine learning approaches. We had some problems in the previous years to get this approach because of these prescribed operations, because of operational problems, because of a lot of interaction that we have among wells. So we are developing new ways to get better results from machine learning forecasts. One of the ways is using filters, and these filters will consider all the restrictions of the operations, all the prescribed operations, and also all the rules that we get from the optimization. So the machine learning algorithms will not understand that we are going to do, for example, a prescribed operation to close the well or something like this, so we have to impose these solutions. And then we are also using hybrid approaches where we use the probabilistic studies from the model base to feed information to the machine learning. So once we did these two things, now the predictions of the machine learning is much better than before, and we can use them to help in the real-time optimization. I'm going to show a little bit of the results of the two-stage optimization, stage 1 and 2. And the stage 3 you are working nowadays, probably next year we'll show you some results of that. At the end, when we finish all this and we can do this automatically, we hope to have a digital twin of the field we are working on. So, as a summary of what we did so far, improvements in the data simulation, lifecycle optimization, short-term, and digital transformation. For data simulation, the most important part was that we had to change the way we are doing data simulation and give much more attention to the productivity and injectivity of the wells, because this is what makes the change in the short term. For lifecycle optimization, we had to develop new ways to optimize the lifecycle optimization because we need to do it much faster than before, and we don't want to get the best solution. We want to get an approximate solution at this point because the real optimization will be done in the short term. And we work also in parallel to work on this much more complete optimization process that we will run offline. And every time we have a new solution, I can go back to the short term. For the short term, we had to develop new ways to integrate with the optimization of the life cycle optimization. The optimization is much faster and much easier to do because we don't have many variables that we are going to change in the next loop. And once we get the solutions, we go to the real-time implementation. And now we are developing the digital twin, which is we have to monitor the results. We have to automate and integrate all the three processes, the three stages. And once we finish that, we are ready to go. The example I'm going to show is a particular field in Brazil, the pre-salt of Brazil, which is a very huge field with injection of CO2 and gas. And to perform a complete optimization process, life cycle optimization, would take us about 6 months. We have a calculation to know how much time we're going to use to consider all the uncertainties, all the models, all the simulation, because the simulation is very time-consuming, and so on, it would take 6 months. So we are developing a lot of techniques to get approximate solutions with less bias as we can. Instead of using 6 months, we did, in this case, in a few days, the optimization. We know that it's not the best solution, but it's a best solution we can get to provide to stage 2. Some simplifications we can use is lower fidelity models, we can use proxies, we can use less representative models, we can use less samples per iteration in the optimization process. Instead of running 30 years, which is the prediction for this case, we run a few years back, which is about half of the time for simulation, and we can use other simplifications to do it faster. In this case, instead of 6 months, we did in a few days. We performed the 12 steps that I've been presenting, also I presented last year, the 2 steps to reservoir characterization, the 3 steps from the data simulation. In this case, we get 47 representative models there. And then the blue steps to get the best life cycle optimization process. And now we are performing the 12th step, which is the short-term optimization. Here's just an example. After performing this life cycle optimization, we perform an optimization of the closed loop cycle optimization, the short term. Of course, the results will not increase 20%, 30% because just a cycle. So if you get 2% or 1%, 3% is good enough because we are just improving the next 6 months of the field. Consider the entire NPV, for example, 2% will be a very good result for changing the variables only in 6 months. And in the left graph there, I have the influence of this optimization process in the cycle. And then I check for the life cycle, for entire life of the field in the right part. That meaning that the solution I got from the short term is also good for life cycle. So I'm ready to implement this in the field. If the solutions that I change in the short term, if I move it to the life cycle and it's not good, then I have to do something because there are some operations that are good for short term but not good for long term. So I have to be very careful in that. And in this case, the same solution I applied the short term was a good solution for life cycle, so we were free to go. Of course, here I'm checking the risk curves of the problem, considering all the uncertainties, all the representative models in the left graphs there. And the top part is the short-term effects, and the bottom part is the life cycle effects. In the left part are the representative models. We have 9 representative models in this case. And in the right part is the full ensemble. In this case, it was very easy to decide because all the management that we changed for short term was good also for long term and was good for almost the full ensemble of the models. So I was confident that the change will have to be done. In some cases, that's not really the true because some effects of short term can be different from long term, and then I have to decide which one I have to go through. And after the stage 2, then we are performing the real-time optimization. I'm showing here just an example of what type of operation we can have, and we have to change the operations. For example, in the top part here, I have an increase in the oil production because some other well is closing, and as they are connecting the production facilities, the production increases every time if I close another well. So I have to be careful with this type of operations. So when well closes, I have to do some changes in the operation. We have also in the pre-salt there the second wave wells. Every time a new well enters, the rates of the other wells decrease because we are operating all the time in the gas production restriction. And also I have a lot of closing of the well because of pumps and other operational problems. And so every time I have this type of modification, I have to change the solutions. And our stage 3 is dedicated to do exactly that. I have to be careful in how we're going to change the solutions to not to jeopardize the best solution we have. So in summary, I do this complete optimization process much faster. I do a complete optimization process offline. Then I feed back the solutions to the stage 2. In the stage 2, I perform a much faster optimization algorithms and much faster to get a good solutions for the short term. And every time I have operational noise can be anything that is not expected, I do a real-time optimization. We are doing that now some graphically, trying to show the users how to operate them. But of course, at the end, we want to do everything automatic. But this, for example, is just an example how the user can see the diagnosis of the problems. In this case, you can see in red in the between there that I impose the solutions to the simulator, and the simulator is saying that the gas that's being produced cannot be reinjected. So I have to do something because in this case, the pre-salt fields, all the gas and CO2 that's produced have to be reinjected. So I have to change anything in the injectors or producers, and the real time will do exactly that. I will have all the sensitivity analysis of the injectors and producers and the interaction between the producers and injectors. So I will change the operations in producers or injectors or in the cycle of the injection of water or gas, anything that I have to do to solve this problem. And the user can also monitor, in this case, is 6 days of history data and 60 days of forecasts, so we can see if the solution is good or bad. And also check, we have a production monitoring where we can check all the producers, what's happening for the producers. And every time I have a change, in this case, for example, we have a P16 shut-in, and one P16 shut-in, we have to do a change in operation and other wells in order to produce more and use the full capacity of the platform. Here's the same thing, just showing what we're going to do. And now we are building this. We are confident that the forecast is good, and they have a way to do a good forecast and do good optimization process. And we are working on the real-time optimization. The real-time optimization will be based on the interaction between 2 producers, 2 injectors, or a production injector. We have a matrix of the influence of each well in another well. The producers are connected not only from the reservoir, but also from the first surface facilities, especially in the pre-salt, because they are operating the full capacity of the platform all the time. And when we have a noise, for example, that we are showing this graph, when a well is shut-in or a new well opens or anything that is not expected, I have to react very fast. So I go into this matrix and decide the best well, or best injector, or best producer to change. And of course, in this real-time optimization, we can also include that we are doing nowadays other objective functions like carbon intensity calculation, energy calculation, or other objective functions that we can use to optimize the reservoir. So at the end, we are improving our 12 steps methodology in order to include the short-term analysis for that. Our main applications, the real giant fields from the pre-salt, in this case with permanent 4G and ICVs, intelligent completions, WAG CO2 injection, and what we call gas-driven optimization, because the gas is operating the full capacity all the time. We have worked on the 4 colors of our closed-loop methodology. We had to improve the quality of the models, especially for the forecast of short term. They are a little bit different from the life cycle. We can use multi-fidelity models in this approach. We can use a model to life cycle optimization and a different model for the short-term optimization. We had to improve a lot the data simulation process to improve the quality of the model, considering productivity and injectivity. This is the most important part. Without that, nothing will work because the errors are very big in our current simulation models. We have to make sure that the productivity and injectivities are very well calibrated in these red parts. And for the forecast and decisions, I think the most important is that we divide this in 3 stages and try to work adequately in each stage of the process. Once we finish that, we're going to test in other models as well. So as always Energy asks us to do, so what is contribution to industry? I think we are trying to develop better use methodology for a better use of reservoir models, to do a better reservoir management, considering not only the life cycle, but also short-term effects. Digital field analysis, including machine learning techniques to help us to complete the analysis of this model-based analysis. And when we finish that, I hope to have a methodology to have a digital twin of the reservoir where we can decide very fast how to operate the field. At the end, important step towards the more efficient energy production. With that, I would like to acknowledge all my group and researchers, students, professors, IT, and that help us in this getting these results. Thank you for the sponsors and especially for Energi Simulation.
Thank you, Dr. Schiozer. Any questions from the floor here? Dr. Haji Beji. Hydrogen, right?
It comes somehow implicitly unbiased anyhow about this. I try to avoid the word hydrogen, but my question is relevant to that, obviously. So thanks a lot, Denis, for this interesting talk. So if you forget about production data and for the new systems like this thing that Andrew just mentioned, we work more on the mechanics as well and the cyclicity, time dependency, etc. And detecting the stress distribution in the subsurface region is very important. For that, you get kind of a spatial data of your reservoir, whether from seismic or from any other monitoring schemes, that then the resolution of the data is different than the resolution of the simulation that you run. Now you have, let's say, vague, coarse scale data, and you want to run fine scale simulation in the best case scenario. So the mismatch between the resolution of the data, especially multi-source data, well logs, wells, and also field, and fitting them into one single simulation scale or resolution. How would you target this challenge of mismatch of the resolutions between observation and what we expect as modeling simulation to be actually sensitive about?
Okay, in my opinion, at least what we are trying to do is to have different models for different objectives. These effects that you are talking about are very important for some objectives, but not very important for other objectives. So
absolutely.
For life cycle objectives, these are very important because all these effects and uncertainties related to these things that we are talking about will play a major role in the response. So I have to know how to manage them. But for short-term effects, maybe these are not so important. So I can use coarser models and simplified models to just, for example, how to operate the fields in the day-to-day basis. Maybe these are not so important. That's why we are trying to develop methodology to use different fidelity models.
Sure, but then it would be the priori or some sort of in advance decision about what quality your simulator should have, right? And then trying to make it work. Is that what you would do? So then you would preset lots of parameters like the resolution, etc., and you would say, well, let me just fix the permeability and other things to match the data, and I have enough degrees of freedom to do that. You wouldn't change the grid resolution of your simulator or other things just...
Yeah, I'm not changing the degree of the freedom of the simulation or the grid size and anything. I'm doing different models in different stages here. For example, I can use a very complex model with a lot of detail in this offline running this life cycle optimization. Every time I find a new solution, I can input this new other model, which is much coarser and much faster to do it life cycle. Sure. That's the idea, because it's very difficult to exchange data between different models, models. So I'm not doing that. I'm just selecting different models for each objective and running in parallel. And if good solutions appear, I can feedback the other model with the new solution.
Excellent. No,
that's the idea, to avoid these complications that I know that's very complex.
Yeah, that's very good. Thanks.
Thank you. Well, actually, I have a... Whoops.
Go ahead.
Let's try that first.
Okay, Des, I had a question. I enjoyed your talk. You talked about simulating the data, in particular the injectivity and productivities of the wells, so matching liquid rates, but do you also deal with matching water cuts and GORs through the whole history matching process?
Yeah, the history matching, I didn't change anything, but I add some objectives with a higher weight, which are the variables related to productivity and injectivity. because this will have to be very well calibrated. For long-term effects, the productivity and injectivity are not so important, because at long time they will produce more or less the same in their drainage area and so on. But for short-term effects, they can give you 50% errors or something that are very different from the real behavior. So there is no meaning in optimizing the short term if your productivity is completely wrong, right? And when you do data simulation with a lot of ensemble of 100, 200 models, each model has a different productivity injectivity, so we have to calibrate them very carefully. And then for short term, we are now using just one model. We are using deterministic, so it's much easier. I calibrate exactly the productivity because I know how much is the productivity or injectivity based on tests, and then I do that differently. So I have to do that very carefully, because otherwise there is no sense in optimizing short term with wrong productivity injectivities.
Okay, good, thanks.
Okay, thank you, Dr. Rod Padaky of Stream Sim Technologies. It's close to the end of your talk and question, but I basically can, in a way, summarize the questions that I would have as well. Is how much confidence do you have after history matching, water cut, GOR, everything else, 3,000 days of history from what I could see, and you're using a deterministic model of a geo model and multiple resolutions and whatnot. What's the confidence level on a geo model at this point in time?
The confidence model doesn't change for life cycle process.
I know. Like, are you quite, say, 90% confident that your geo model that you're using is robust enough, representative enough of the true geology? Mm-hmm. Or are you kind of still 50-50, wondering, there may be surprises based on production, and you have to make some changes, as one would mention about changing the perm, get a match, and go forward, almost once in a while. Mm-hmm. So how much confidence do you have in the geo model? Yeah,
the idea is it depends on how much data you have and how much history you have. But the idea is we are not changing this part. We are confident that the models are good, but we may get surprises, and that's exactly what we are trying to do. For example, if I did not predict a water breakthrough, for example, and I'm imagining the short term without any breakthrough, and then the breakthrough occurs, I go to real-time optimization, because everything changed. I have to change completely the operation because I have a new situation. And what we do is, after we do this, we change the operation immediately in the real-time optimization. Then we feed back the life cycle optimization process to improve the quality of the models. And in parallel, I can find better solutions. So I keep running these 3 stages in parallel, and we can go from one to another.
Okay, thank you. Once again, thank you very much for your talk.
You're welcome.